We'll wait for a couple of more minutes. So maybe if somebody is late, they'll be able to join. Meanwhile, I think Fanindra is joining us for the first time today. Um, has everyone received yesterday's email in which I shared the class lectures for those who were not able to access ISSS?
Yeah, I have received it, the email.
Oh, okay, great. So I've been asking ISSS to register the students who wanted to join after the deadline of the registration. So I'm not receiving any response from them. But meanwhile, to avoid this issue in sharing of resources, I'll be sharing the recordings via MS Stream. So probably you won't be able to download it. Also, ISSS has requested me not to let students download these lectures, and they have restricted to upload it on YouTube as well. So I hope the MS Streams interface is fine to you. And meanwhile, I'll look into what has to be done to get you registered.
Yeah, that is fine. That is fine.
And the notes are available on my Google site, so I'll be sharing them over there.
Yeah, I've looked into it. Yeah, thanks.
So whoever has missed the previous two lectures, the first one was just discussion on the basic electromagnetic theory. The second lecture, we started with the finite difference time domain method. We discussed some points, especially the formulation of the update equation for electric field and magnetic field. I'll recommend you to go through it if you have not gone through it yet. We'll briefly recapitulate what we discussed in last class, and then we'll begin today's lecture. So we'll wait for a couple of more minutes. I see a few of you joined now, so maybe somebody else is running late. Okay. Like, are you guys, whoever is being able to access the ISSS site, are you facing any difficulties? Hmm. So I guess not. You are able to find the slides and the lectures, right, on the ISSS portal.
Yes, I can access the videos and the files.
Okay, thanks. Okay, maybe we'll start now. Okay, so this is the course outline, and the module one we did in the first class. We started with the module two the last class, and today also we'll be discussing module two, and we'll try to finish it today. So today's lecture will be is mostly borrowed from book by D.M. Sullivan. Heads up for that. So maybe if you have any doubts regarding today's lecture, you can refer to the full text from this book. Can refer to this book. This is, oh, where is it? Okay, yeah, this one, this particular one. So it is also available in mm, Python and MATLAB as well. So whatever language you prefer. So the first module we went over the basics of EM theory. The second module we are still here, which discussed till here. Today we'll cover all these things. So in the last class, we discussed about the partial differential equations, the central difference scheme, the approximation using finite difference technique, the little discussion on implicit and explicit method, We saw a brief history of FDTD, talked about Professor E. Um, Little discussion on the convergence and accuracy of the FDTD method, the basic solution procedure in FDTD method. So you don't have to worry about most of these things. We'll go one by one, and once you start running your codes, it will become more clear. So today we'll discuss the code as well. We'll go through it line by line. I show the code on my screen and we can have a discussion. And then we did discuss about the one-dimensional free space simulation. We developed the E and H update equations. I showed you some simulation as well, the plots. We discussed about the Gaussian source and yeah. So we'll do a brief recapitulation of the last class. So So we started with the curl equations from Maxwell. We chose we are since we are like concerned about the 1D for 1D only. So for the upper wave propagating in z direction, we have Ex and Hy. So these are the Maxwell's equation for a wave propagating in z direction. Taking the central difference approximation for this set of equations. So this was the formula that we discussed in the last class for central difference. We achieved the couple of equations for E and H. So where N and T are the time step and distance. So this so for the electric fields differential equation, finite difference in time, uh, we take for a time step delta t, we get for the electric field at n, we take the we use we use the values at n plus half and n minus half. Similarly, for magnetic fields differential equation in terms of z, we use the for the magnetic field's value at time instant n, we use the values of magnetic field at k plus half and k minus half. And once we have the central difference approximation for electric field and magnetic field, we substitute them and we achieve the finite difference approximation of the first Maxwell's equation. Similarly, for magnetic field differential equation in terms of time, we for a time instant n plus half, we use the value for it. We use the values of magnetic field at n plus 1 and n for the position k plus half. So, and for the electric field, uh, differential equation in terms of z, we use the values of electric field at k plus 1 and k for a time instant n plus half. And once we have this, the value for electric field and magnetic field, we substitute them and we get the approximate differential equation for the second Maxwell's equation. So once we got the central difference approximation for the two Maxwell's equation for a wave propagating in for a one-dimensional space propagating in z direction, we have we get once we have this set of equations, we rearrange it for using for delta t and delta x such that the latest electric field and magnetic field are on the left hand side, and we achieve the electric field in terms of a past value of the electric field at the same position, and in terms of magnetic field, so in terms of the surrounding magnetic field values for past time, and for the we achieve the magnetic field at for the latest position for the latest time in terms of the magnetic field for a past value and the electric field of the surrounding values once we have these update equations, uh, we know then normalized it for to reduce the difference in order for electric field and magnetic field for simplicity of our computation, and then substituting this particular substituting this particular value for electric field, we get the final update equations, and uh, uh, then using this particular update equation. Okay, then we had discussed about how we choose the time step. So once we had the value of the times, uh, when we if we had the cell size delta x, we calculate the time step given by this equation, which follows the Courant limit. We'll discuss the Courant limit today, and we had so we using this particular equation, if we substitute the value of delta t over here, we get this particular equation equals to half, and by substituting this inside, so over here this coefficient, this once we substitute this uh, from equal to half, then we get this final update equation, which is compatible for MATLAB or Python. So the last class, this was the major portion that we covered. So I'll pause here and take any questions that you have from last class, and whatever we just went through. So all this was discussed in the last class. Do you have any questions? Any questions from the previous slides? Jay, any questions? Priyank?
Not now. We can move forward. Yeah.
Oh, okay. So
Yeah, it's fine for me also. Yeah.
okay, great. Also, in the last class, we saw what is a Gaussian pulse, how it is expressed in frequency and time domain, and we use this Gaussian pulse for a simulation, and we observe this using the same update equations and giving a Gaussian pulse in time domain. We had achieved this particular simulation where a pulse travels towards the boundaries and gets reflected, because we don't have proper absorbing boundary conditions on both the edges of the simulation space. So since this is a one-dimensional simulation, we have two boundaries, and both the boundaries do not have proper matching conditions. So the wave gets reflected, and upon providing proper boundary conditions, the propagating pulse gets absorbed. So this was all which was covered in yesterday's class. We'll begin today with what I mean by FDTD. So since up till now we have discussed some things about the finite difference time domain method. Also, somebody asked in the last class, like why do we call it FDTD? So in FDTD we divide the solution region into a grid of nodes, which we saw, and we approximate the derivatives, the partial differential equations using finite differences at the various nodes. Hence the first part of the name of the finite difference time domain comes from the finite differences, and the second part is due to the use of time domain method of the governing equation. So we started with the Maxwell's equation in the time domain form, and we used the finite difference scheme, especially the central difference scheme in for our case. So hence the name finite difference time domain. And yes, so the result, the formulation is pretty simple, especially when once you start translating the update equations from the, the central difference scheme to your MATLAB or Python code, the things seem pretty straightforward. So we'll discuss a little about the stability of the FDTD method. So any EM wave propagating in free space cannot go faster than the speed of light. So for to propagate a distance of one cell, which is given by delta x, the minimum time should be delta t equals delta x by c naught, where c naught is the speed of the uh, wave in vacuum. So for a 2D simulation, we must allow the propagation in diagonal direction. So in the in the second module or until now, we are only concerned about 1D. So the first point is what we're concerned now. But in the coming classes, when we go to module 4, where we'll discuss about 2D, so over there we'll have to keep in mind that the wave could be propagating diagonally across in the simulation space. So we'll have to consider the minimum distance as the delta x by root 2. So this is the case for if the wave for a 2D simulation space where the plane wave could be hitting it diagonally, and so for a if our the if our nodes are separated by delta x uh, uh, in x and y direction, we have square grids. Then the and we since we are calculating the electric fields at if we are calculating the fields at these edges in the Yee cell, we'll be calculating the magnetic field over here, or if we are calculating the magnetic fields on these two nodes, then we'll be calculating the electric field over here. So for so we'll have to consider this as the minimum direction, minimum uh, uh, distance that wave is so we'll have to consider this distance for while calculating the minimum time. So this particular distance is given by delta x by root 2, and using this we will get the we get the delta t equals delta x by root 2 c naught. So this is actually the limit, and we usually prefer to keep delta t even less than this value. So this is the Courant limit for 1D. This is the Courant limit for 2D. And similarly, we for the Courant limit for 3D is given by this expression. So I see a hand over here. Yes, Jay. Yeah,
Yeah, so here,
please go ahead.
you have selected a rectangular or a square. So the least part is along the diagonal, yes. But in some cases, we
Yes.
select the hexagonal or triangular. So in that case, also diagonally, right? Isn't it?
Uh, in finite difference time domain method, as far as I'm aware, we choose rectangular or square meshes or cubic meshes.
Oh,
Finite difference, the frequency domain method, usually where the meshing is done prior to the simulation, we usually go for triangular or hexagonal meshes. But in finite difference time domain technique, we don't explicitly do meshing of the simulation space. We choose the delta t and delta x, and the simulation is run at once. So we don't mesh the region beforehand. The minimum time
oh,
step and minimum cell space is specified, and it is implicit inside during the simulation. But yes,
mm,
in frequency domain method mostly, or methods in which we mesh the region beforehand, there we use triangular and hexagonal shapes. Yes, any follow-up questions on that?
No, that's fine. Thanks.
Okay. So yes, in finite difference time domain method, we used rectangular or square meshes. Mostly we use square meshes because introducing a rectangular mesh or a cuboidal mesh can be more complicated. So we use square or cubic meshes. So hence yeah. So any other questions, anyone? Hmm. Okay, then we'll proceed. This is the Courant limit for 1D. This is the Courant limit for 2D. This is the Courant limit for 3D. Uh, Maybe it will be a good exercise if you try to calculate this. So this is summarized by the Courant condition. This is very popular. We For the scope of this particular course, will not much discuss about the Courant condition because we are looking forward to implementing it. So as long as you follow the Courant condition, your code will remain stable. So for a generalized space, the Courant condition, we can give the Courant condition by this expression, and it will be a good idea if you keep instead of keeping it equal, you keep the delta t always less than now, because uh, keeping the time step smaller is not an issue. But if you work close to the Courant limit, or if you violate it, your code, the errors in your code will not be bounded and they will multiply. So maybe it will be a good exercise when if when at the end of today's class, I'll provide you with the code. Maybe you can try violating the Courant limit and see what happens. Okay. So we had seen in the simulation, when we included we did not had the boundary conditions. The waves were getting reflected from the boundaries. So it is essential that we provide a boundary condition so that our simulation space is not affected by the reflections coming from the boundary. So normally when we calculate the E field or the H field, we use the value of the E field or the H field and the neighboring values. So this was the set of update equation that we had achieved. Now what happens at the edges? At the edges, for example, if our edge is at k equal to 1 or k equal to 100, the value if we are for electric field at the edge, for if we are calculating at 1, we will need the value of magnetic field at h equal to 0, which is not in the simulation space. So uh, for our code, we'll have to specify the value, which we'll have to specify this particular value. And this has to be done such that no garbage value or 0 is brought into this particular equation, which will result in erroneous calculation. Similarly, for magnetic field, if we are calculating near the boundary, we'll need the value of electric. For example, if we are at one of the boundaries on the other side, where, for example, the boundary is at at k equal to 100, we'll need the value at 100 equal to 101, which we do not have in our simulation space. So we'll have to adjust the boundary such that this particular value is fed properly and we do not achieve any erroneous result from this particular update equation. So, for the update equations within the simulation space, this particular set of equations suffices for the E and H field. But at the boundaries, we have to define it explicitly such that they do not introduce errors. So we'll have to estimate what should be the value that has to be fed at the edges, and in doing that, we we since we are defining the simulation space, we know at which points we have the boundaries, and we explicitly then we will explicitly calculate the like estimate the values which should be fed at the boundaries, and do and we feed it by ourselves. So over here the absorbing boundary conditions are like physically they do not mean anything. We are matching it numerically. In the fourth module where we'll discuss PML, that is perfectly matched layer. The concept behind the PML is will be very different from this absorbing boundary condition. Over there, we'll use the concept of losses to match the boundaries, but over here, the this particular matching is done only numerically. So for a boundary condition at the end where k is equal to 0, if a wave is going towards a boundary in free space, it will be traveling at c naught. So we since our simulation is being done in free space, we know the velocity of the wave, which is c naught. We know where the boundary is, that is k equal to 0. So we will calculate how much distance the wave travels in one time step. So the distance traveled in one time step can be calculated by multiplying the waves speed of the wave with the time, and we get that in one time step the distance traveled is delta x by 2, which is cell length by 2. So we have achieved now we know that in one time step the wave travels a half cell distance. So so we know that it will take two time steps to for the wave to reach from one node to the next node. So in delta t time, if the wave travels delta x by 2 distance, then in 2 delta t time the wave will travel delta x distance. So it takes two time steps to cross one cell. So matching it numerically is very easy. So what we do is that we take the value of electric field at cell position 1 for a and for a time for a time of past instants. Uh, so for n equal to minus 2, when the value at the electric field should travel to equal the cell position at equal to for a cell position at 0 at n. That is the value at position 1 will move to the value at position 0 after two time instants. So we instead of letting the code simulate normally at the boundaries, we define this ourselves. So this is the boundary condition for electric field, and doing so we don't and once we have included this particular equation in our simulation space, we do not calculate the electric field value at equal to 0 because we are explicitly defining it. And implementing it in code is also very easy. We take a temporary variable and we substitute it. So this is the boundary condition implementation in MATLAB. So we what we did is we took the electric field value uh, at yeah so we took the electric field value at position 2, assigned it to a temporary variable. Then and the next time instant what happens is when this value is updated, this particular value is fed over here, again the next value is fed over here, and this particular value is then fed over here. So after two time instants this particular value reaches this value, and in MATLAB the array indices or vectors start from 1. So we do not have any indices equal to 0. So this is the boundary condition implementation on one edge, and similarly we do it for the other edge. So this was all about the boundary conditions. We'll stop here and I'll let you read it. And if you have any questions, we can discuss now.
This part is still not clear to me when you said um, it takes two time steps for the field to cross one cell. So it is so you make it ex n 0 is equal to ex n minus 2 at 1. So how is this case? It takes two time steps for the field to cross one cells.
Okay. I'll try to do something.
Um,
Yeah, I don't have. Okay, maybe I'll try to write it. So, example, this is our simulation space, and this is the boundary, and this is the cell next to it. So, this is at the position 0, and this is at position 1, and the wave is traveling with this particular this at c naught, and in one time instant, the distance covered by wave is delta x. So, is this clear? Like, how did we get achieve this?
yeah, this is fine to me.
This is fine. So for delta t times, for in delta t time, we travel delta x by 2. So in 2 delta t times, we will travel delta x distance. Is this clear?
I see. Okay. Yeah.
So what happens is in 2 delta t times, the value of electric field over here is transferred to this particular node.
Hmm.
Okay, so after two time steps, the value of electric field is transferred over here. But at the boundaries, we do not have the sufficient. We do not have the values of magnetic field over here. So instead of running the update equations, what we do is we manually put this particular value over here. So what do
I
we do is we record this value and then substitute it after 2 time instant.
okay. I got it now. Okay. Great.
So this is why I said before that this does not have any physical significance. What we are doing is we are matching it numerically, because we know that after this particular instant the electric field value should be this. So we explicitly do that at the boundaries, and instead of running the update equations. So this is a very simplified form of Moore's boundary condition, Moore's absorbing boundary condition. So Moore has given this boundary condition, and what he gave was more general. But for this class, we will restrict ourselves to a very simplified form of this boundary condition. And to implement this, we are using this set of equations. So this is for the first, if so, for example, if this is our simulation space, so for this edge, we are using this three equation, and for this edge, we are using these three equations. So over here, for example, if KE, this is KE, this is the KE node, the edge, and this is the beginning. So this in MATLAB we do not have zero, so we'll say it as one. So this is what we do. So since we have to put the value of electric field of the of for past second instant, so we meanwhile we'll have to store the value, because after and we are not storing the electric field values in time. So what do we do is we store the value at 2 in this variable, and over here, and then in the next instant when this particular value gets updated, it is again stored over here, but this value at the in the timing translates over here, and when again this is updated over here, this value updates over here, uh, and this value has already been updated over here, so at the boundary we are updating it, and this goes on.
Okay, so this kind of
I hope.
MATLAB we do only at the boundaries. Okay, so for inner
Yeah. So
cells. Okay, okay.
yeah, this is done only at the boundary,
Mm.
not for the entire code. So when we write the code, we won't be writing the electric field value, like the updating in the for the electric field at this value. We won't be running it. Similarly, for the electric field value at the other edge as well, we won't be running the update equation at this particular node. We'll run it till here, and we'll use this value over here.
Okay, very nice. Thanks.
Anybody else? Any questions? So in literature, you will find many ways to like perform boundary conditions. You will there are a lot of groups have given a lot of techniques, and since we are starting with FDTD, we are using the simplest one. This is not the best one, but this is the simplest one. So if you remove the constraints of the code, which I'll show next, you will see that this is not working perfectly. So you'll have very small reflections, but reflections will be there. So because we are doing it uh, numerically, so and there will always be small errors. And if you reduce the scale of your graph, you will be able to see the little mismatches. But it will be very small and won't really affect much of our simulation space. And for begin starting with it, it's fine. So once you are able to do this, maybe when you write your next code, you will use a better boundary condition. So I'll wait for some more time and let everyone read it. And if you have any questions, we can take now.
Hello.
Yes, Priyank.
Yeah. So I have one general question, like where exactly the modification part coming into the picture? Like here we are defining the cell, we are defining the width of the cell, and we are writing the Maxwell equation. But where exactly, like in research point of view, where exactly the modification is coming? Like uh, which part, like before defining this cell we have to write the Maxwell equation, so it is inside the Maxwell equation we are like modifying it, or in cells itself we are modifying means? So
Uh,
yeah,
eh, I could not follow your question. Is what is this modification for the boundary
modification,
conditions?
yeah, suppose instead of state device, like some state cell, if we have some curvature kind of thing, so there again we are defining in terms of square waveguide, or we are modifying the Maxwell equation and we are transferring from curve to the square conversion, and then we are again doing in the square meshes itself. So what exactly we are doing? We are changing the mesh, or we are changing the Maxwell equations? So
Oh, no, 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 we do not change the Maxwell's equations. So your question is what do we do if we, for example, if we had a circle or if we had a sphere, right?
yeah, if we
If we
have
had a
some
sphere.
curve kind of waveguide or some curvature, yeah.
Yes. So right now, what we are looking at is it is a 1D problem. So even if it was a circle, so if we the circle, so for us it will be just like this. So there is free space. Then there is, for example, this material. Let's call it dielectric D, and then again free space. So for 1D, what we'll see is we have this particular region as free space, then we have this dielectric, and then again we have this free space. So we are looking at it in 1D. So it so our problem statement will simplify it to just this particular set. But when we move towards 2D, what we'll have is this we'll see the sphere as a circle. So there will be this dielectric, there will be this free space, this will be free space, and this will be in 2 dimensions. So in the two dimensions again, we'll use square meshes. The square, like we do not explicitly call it meshes because we are not meshing it. We are just dividing the solution region in squares. So we'll have this particular in this way our region will be divided, and then we'll be calculating the electric field over here, electric field over here, and in bit electric field over here, electric field over here, and magnetic field, for example, over here in between the magnetic field over here. And for the entire region, we'll run the code and we'll simulate it. So your circle will uh, lie in this particular region. And when we move towards 3D, uh, then we'll be able to capture your sphere more properly. And over there, we'll be using cubic cells, like the cubic Yee cells. So then we'll be calculating the electric field at the nodes of the cell and the magnetic field on the surfaces of the unit cells. So right now, if our even if our like the if we had to simulate some dielectric, it will reduce just to like a line segment. Was I able to answer your question? Like any follow-up
Yes, I
questions on
completely.
that?
No.
So it was like rightly pointed out that right now we are just looking at a problem space in 1D. I see a hand over here. Yes, Abhishek.
In this, can you hear me?
Yes, yes. Please continue.
In this particular slide, we have taken time step to be delta x upon 2c0.
Yes,
This is for FDTD, but however, it should be the current limit is delta x by c0, na? So we need to keep it less than that. So we have taken this.
yes. So if okay, this how do I get out of this? Do you want this scribble to be here, or should I discard it?
We can
Let's keep
discard
it.
it. Let's keep it.
Okay. Um, okay. So over here we discussed that the Courant limit is
For 1D, it is
given
delta
by
x by c0.
C0. But as I had expressed over here, that it is better if you keep it less than this, because less is not an issue, but if you exceed it, you will see some irregularity in the code, and hence I'll give the code today, and uh, it will be a very good idea if you try to execute it above and below. And if what happens if you make this very much greater than the right hand side and very much less than right hand side.
So in FDTD, we generally keep it delta x by 20, right? Well, that is our approximation. Or
Yeah, we for to keep it very simple, I'm keeping, instead of keeping it as C0, we are keeping it as 2C0. 3C0, 4C0, all is fine. But then again, for the boundary conditions, we'll have to store more values at the edges.
understood. Thank you.
Okay. And any more questions? Else we'll move forward. Okay, then we'll move forward. Now, while discussing the Courant limit, we chose a delta x, we chose the cell size, and then we calculated the time step. Now, how do we choose this cell size? So choosing a cell size for FDD it is an approximation procedure. So it is up to you how you choose it, but we should keep the cell size such that uh, such uh, that we are adequately representing the wave which is propagating through it. And a good rule of thumb is keeping 10 points per wavelength. I think when all of us have during some point of the other, we notice that we, whenever approximating a wavelength, we or determining the electrical size of a device, we choose we see that if it is less than lambda by 10, we assume it that it is electrically small, or lambda by 50, right? So a good rule of thumb is keeping 10 points per wavelength, but if you use more points, you will be better able to approximate the wave. For example, if we had a sine wave, and if we just chose 2 points, for example, over here and over here, if you're choosing 2 points, then it could have just been a triangular wave, and we have not made a very good approximation. And if we start increasing the number of points, we start increasing the, we start to get a better approximation of the wave propagating through the simulation space. So 10 points per wavelength is good. Using more is better. But then again, you have a limit for your the device on which you are running your code. It will have its limits. If you use a smaller delta x, the number of, and you want to simulate for example, 1 meter of simulation region. If you use smaller delta x, you will have more nodes, and then again the simulation time will increase because you're running your code for more number of points. Then okay, so I hope you get the gist of it. So here for example, if we are running simulation with the 400 megahertz wave, the frequency of the wave propagating through the simulation space is 400 megahertz, and and it is in free space. So we calculate the wavelength. So this velocity of the light in free space. This is the frequency. We get the wavelength as 0.75 meter. So approximating it, so we choose lambda naught by 10. So this is our lambda naught, and we get delta x equal to 7.5 centimeter. So this is our delta x. Any questions? Maybe no. So, and what happens if it is not free space? So if it is not free space, and we have, for example, if we are simulating it for a biological tissue, then we'll have a lot of different regions with different dielectric constants. So what we'll do is we choose the highest dielectric constant, because for this we will have this shortest wavelength. So for example, if our simulation space has muscle, which has a dielectric constant of 50, and the wave again is at 400 megahertz, then we calculate the lambda naught according to this particular dielectric constant. So we know that v is equals to c by root under mu r epsilon r. Okay, so again mu is 1 and epsilon r is 50, so we take root 50 over here. We perform calculations, and now what we have is our the wavelength is 10.6 centimeter. And for this particular lambda naught, we will take the cell size of 1 centimeter. So 10.6 by 10 is 1.06, and like it is better if you even keep it smaller than this. So let's take it 1 centimeter. No issue in taking a smaller cell, but again you will you have to use your code will use more time or need a better system. So any questions on how we determine the cell size, and the how we get the time step from the cell size using the Courant limit?
And so I think this cell size will be constant. For example, this muscle cell are surrounded by free space. That means it's a combination of both free space and the dielectric. Then
Yes.
this will be the constant for throughout the structure, isn't it?
Yes. Yeah, you can probably try to. You can also use a bigger cell for the free space region and smaller for the muscle tissue region, but it will only complicate the problem, the simulation space. So it is better you use a constant throughout it. So for our simulation space, we generally take the cell size for the highest electric constant. Okay, so we'll proceed. Any questions? Any questions, Priyank, Pratnesh? Okay, well, so up till now we have gone through all the requirements that we needed to write our first code. So the code is not very long. So with all the indentation spaces, it ends at in 67 lines, and we'll discuss the code now, and I'll share this code with you and you can maybe run this. You can run this code. I'll also give you a few questions as your first assignment, which will help you better understand the code. So uh, the first class when we had the poll, we saw that most of you are already familiar with the environment of MATLAB. So this particular set of lines are just to clear the memory, close the already open tabs, and clear the command window. Now we starting the code, we decide how many number of nodes we need in our simulation space. So over here, we take the simulation space with 500 nodes. We assign 250 inside KC, which is the center of the space. So at KC, we'll be inserting our source. We define the epsilon naught, and this is where we define the cell size. The cell size is in meter, so 0.01 is our cell size. Now, following the Courant limit, we calculate the uh, time step, and this is how we determine the space axis. So we will need this especially for plotting our output. These are the set of the set of variables we are defining it for the absorbing boundary conditions. So these are the temporary variables used for the absorbing boundary conditions. Then initializing our electric field and magnetic field. So the electric field and magnetic field are vectors or arrays, and we are initializing it with 0. So this is how you can initialize them in MATLAB. You can also use a loop to do it. Now, for using a Gaussian source, T naught is the time delay, 20 is the spread of the Gaussian pulse. So this is for the source. Okay. Now number of simulation steps. So we define the number of simulation step by ourselves. You can also define the simulation time and then calculate the number of simulation steps required. For example, if you want to simulate it for seconds, okay, 2 seconds, you can divide 2 seconds by dt, and you will get the number of steps. So over here I have directly assigned a simulation time. Now as you're familiar with MATLAB, we need to define a figure window, and this is just for formatting. Then we start with the main part of the code. So from here, we start running the code in time. Any questions for the code till now?
Yeah, I still confused about simulation time. So how do we define simulation time in advance?
For example, like at first, you can take an like since this is a time domain method, and for example, for a simple 1D problem, you want a particular wave to if the source is over here, and if you want the wave to travel to the boundary, come back, and then travel to the boundary, so you can get an approximation of the total time required for it to bounce back between the two boundaries. You can so you should always run the simulation time such that it has at least the wave has at least reached from the source to the boundary, returned to the other boundary, and came back to the source, so which is uh, which is for at least 2 cycles. I don't know what is the issue with my mouse. So you have to run it for at least 2 cycles. Running it for 10 cycles is the best. So running it for 10 cycles is the best, but again, it will require a lot of simulation time. So you should at least run it for 2 cycles. And since you already know the frequency of the impinging wave, you can calculate it manually. And if you need more, and you can since you can obviously see the wave, the simulation of in the simulation window, and if you think you need more simulation time or less simulation time, you can change it. Uh, Essentially, this is an approximation on your side, and I'll recommend you to run for at least 2 cycles.
Hmm. And sorry, I missed the point. How did you calculate 700? Can you please say again? 700?
Okay, over here I have just chosen it like randomly. Like this is not calculated from any values. When I viewed the simulation, I stopped it at 700 so that I don't have a very longer video to show it in the code. You must recall that I showed you 2 windows where a sinusoidal wave starting from the center traveled to the boundary and returned.
Yeah.
I just kept it a value where it would stop, and it does not give me a very long video. Otherwise, I would have nothing on the screen simulating. That's it. So if you want, you can choose it by yourself. It is uh, not a very big deal. You can keep a value or run at least for 2 cycles, like such that the wave starting from the source travels to both the boundaries. Like after reflection, travels to the other boundary. I think that is a good approximation.
Mm. And in the beginning, you have mentioned dt is equal to ddx by 6 into e to the power 10, 8. What is this 6
Yes.
e to the power 8?
Oh, this is actually 2 times C naught.
Oh, I see. 2, 3, 6. Okay. Okay, okay.
Okay. Anybody else? Any questions? Is something there in chat? Okay, I think. So this is all before we start with the like time marching. So we have to uh, initialize the needed variables, and determine the simulation space and the simulation time. Okay, so up till now we have discussed till here in the previous slide. Now we start with the main part of the code. So you must recall we wrote this update equation, and again this update equation from the central difference scheme. Now when we start with the code, and you recall that we discussed in the boundary condition that we leave the boundary. We do not update the electric field on the first edge because we do not have magnetic field's value over here. So we start with the second node and run our uh, loop for the electric fields in this particular region. So for every point, for every node, this k equal to 2, 3 till ke, we are running it, and the electric fields get updated. Then over here we are introducing the source. So okay, so you can ignore this. So for a Gaussian pulse, this is the expression that we had seen. This is e power half t naught minus t divided by sigma square. So this is essentially this over here. So we have seen how we write a Gaussian pulse in time domain. We have directly written it in MATLAB. We had already initialized the time delay and the spread before the main part of the code starts. So and then once we have got this particular value, we have assigned this. We are assigning this in pulse, and we are adding pulse inside this electric field value. So over here we are calling it soft source. We call it a soft source because the value of the source is added to the electric field. If it were if electric field, for example, if Ex was directly assigned equal to pulse, then we call it as hard source. So we'll discuss this later as well. Then we assign the boundary conditions. We already saw this in the um, absorbing boundary condition slides. And then we calculate the magnetic field. So over here, we do not calculate the magnetic field value at Ke because for magnetic field, we do not have the electric field at this particular edge. We do not have the electric field value over here. So that will be able to calculate the magnetic field over here. So we do not calculate the H over here. We do not calculate E over here. And they are taken care of by this absorbing boundary conditions. Then again, we are plotting the electric field values, and we're using the Z as the simulation space. And this is all coloring and design. We in this we define the axis. We include a patch so that you can see where the source is. So this you can study more about patch using the help in MATLAB. The X label, Y label, title, and the font size. And we are using get frame so that in every frame your MATLAB figure window gets updated. So this is all for the main part, and over here the code ends. So this is all for a 1D FDTD code. So any questions on this? We'll pause over here. This is very essential that you understand the code, every line of the code. And need not worry, I'll provide you with this particular .m file. You can directly run it on MATLAB in your own system and play with it. Be very familiar with all the variables. Any confusion in the naming of the variables, you can ask now.
We do not put boundary condition on magnetic field. Sorry, maybe it's basic question.
Okay. So when we let me go back to keep it over here. So Okay, so if you let me use my pointer. Yeah. So for calculating electric field, you need the value of the magnetic field of a node which is on the left hand side to it for 1D case. And at the left hand boundary, we do not have, for example, if you're calculating it at the edge, we do not have a magnetic field value before like on the left hand side of the edge. So we do not calculate the electric field on the leftmost point, on the leftmost boundary. We do not calculate the electric field. We use the absorbing boundary condition. And similarly, for the magnetic field, we on for the right hand boundary, we do not have the electric field value beyond this value of k. For example, when k equal to ke, which is the rightmost point on in a simulation space, we do not have a value at ke plus 1. So what we do, we do not calculate the magnetic field value at k at the rightmost point node in the boundary. We over here we use the absorbing boundary conditions. So what and okay. So over here, so what we do is we are running the magnetic field till ke minus 1 and not at ke. And similarly, we are running the electric field from 2 to k, not and not at k equal to 1. And for both of these cases, this particular set of boundary conditions, they take care of it. They explicitly put the value of electric field and magnetic again electric. They explicitly put the value of electric field at 1 and k such that the values are, over here are updated. Was I able to make it clear? Uh, any follow-up questions on this?
No, no, thanks.
Okay, so when you run this code, you will and you go through it by line at your own pace. I think whatever else doubts that you have will be cleared, and maybe some more doubts will arise. So we'll discuss them in the next class, along with the questions that I'll give you that you can uh, do during this week and maybe till New Year time. We'll discuss them. Okay, so say about simulating different sources, we just saw that we have two kinds of sources, hard source and a soft source. So what are hard source? A hard source is one in which the electric field value is assigned to a particular point, and a soft source is one in which the source value is added to the electric field value at that point. So, let's take a look at what happens if there are two sources and both of them are soft source and hard sources. So, so there are two sources over here, and in case of a hard source, these 2 points also act as PEC. So any wave propagating over here will also get reflected because electric field is being initialized over here. So anything which nothing, so the electric field won't propagate through this point. And over here, so these two are soft sources, and the this particular pulse propagating over here will pass through it because the electric field existing over here, the electric field value over here will be added. Uh, the source value will be added to the pulse generated over here. So these are the like these are the two kinds of sources usually used in finite difference time domain method. Most our cases will be using the soft sources. And up till now, we have seen the use of Gaussian pulse. So if you want to use a sinusoidal pulse, you can change your code with this particular update equation. Over there, we had used e power t minus t naught by sigma square. Instead of that, we are just using a sine function and giving it an input frequency, that the time step and the time instant. And for implementing a soft source, you will just add this pulse value to the electric field at that particular position. For example, if you want to use the source at 5, the that node 5, then you just put the value of the position of the node where you want the pulse to be. Any questions from about hard source, soft source, and using a sinusoidal pulse?
Here in this curve, you mentioned these two looks like black dot is PEC.
Yes.
Okay. So, by the way, how this model looks like? I mean, when you design this like dielectric or PEC, do you have any like dielectric any model in your mind to simulate this?
Okay, so in the coming slides, we'll discuss how do we include a dielectric in this simulation space. Up till now, we have been discussing about free space and sources, and these 2 points are actually you marked it using patch, the function using patch, so that you can see where the sources are located at. And if you do not use a soft source, and if you directly like assign, if you do not you add the source value to the electric field, what happens is the electric field will only be initialized by the value of the this function which you are assigning at. So in case of a Gaussian pulse, what happens is once you have already given out the pulse, it will be initializing it with zeros or values close to zero. So and anything propagating through it will get reflected back. It is again the case of improper update equation, which happens at the boundaries where you are not properly adding a value to the electric field. So it will act as the hard source will act as a metal wall, that is a PEC.
Hmm. Okay.
So okay, maybe I'll use a pen. So for example, if this is a source, right? This is a source, and and we are giving it an excitation of a Gaussian source, Gaussian pulse. So initially, the Gaussian pulse, what does it have? It has values close to zero. Then there is a pulse, and then it is again close to zero. So if you are assigning this value instead of adding over here, what happens? It will first give zeros, then give a pulse value, and then it will start again giving zeros. So what happens is we are, if we do not have this particular equation over here, the pulse will keep on giving zero over here. So what happens is this electric field is always being initialized by E equal to zero, and E equal to zero, we know that what over where do we have E equal to zero? At all PEC interface, electric field is always equal to zero. This is equal to zero. So we if we do not add the pulse value to the electric field, and instead if we directly assign it, if it has zeros, it will always be zero over here. So this will act as a metal wall.
Anand, could you please repeat it? Sorry.
Okay. So what happens over here is, so you can see this particular wave is propagating, right? This, and it passes over here, over this particular point value. But over here, what happened? It was reflected. And this is the case of a hard source. And this is a soft source. Now in soft source, this particular, how do we implement it? We add the source value with the electric field, and for a hard source, we just assign it. E is equals to pulse. Okay, so this is how we implement it. And when we do this, for For example, if you are using a Gaussian source, what it is initially it has values close to zero. Then we have some excitation, and then again goes back to zero. So for the node over here, the node over here, the which is, for example, if this is KC1, so electric field at KC1 is always equal to pulse. So initially, if it is always equal to pulse, it was initially zero. It grows to some value, decreased, and then again it is always close to zero. So what is happening is we are always assigning it with a particular function, and anything. So since we are explicitly assigning it with a function, the update equations that we developed will not work over here, and it will for any electric field value propagating from this node towards this direction, or to this node from this direction, will not propagate through it, rather it will get reflected back. And so this uh, makes it a hard source, and this particular point acts as a metal wall. So the electric field's values propagating from this direction will get reflected over here, because the update equations do not work properly if you are using a hard source.
Oh, no.
Okay, any follow-up questions on this, anyone? So in general, we don't use a hard source. Till now, I've not seen any implementation of this, but this is something available in the literature that we should be aware of, and we use soft sources. Okay, then we'll move forward with the lecture. Now, up till now, we have seen propagation of a wave in free space. We have seen the boundary condition and the inclusion of a source. Now, what do we do? Like someone asked, what if we have a circle or a sphere? So unfortunately, in 1D, it will just be a region. But how do we again do it? Because this particular region is, if it is free space, this particular region will have some dielectric value. And up till now, the Maxwell's equation that we did not consider the value of epsilon r. So to include a dielectric medium, we will consider the relative dielectric constant of the media, and we'll consider. So now we'll use the Maxwell's equation where this particular value has been included. Then again, since now we are looking at a 1D problem, we uh, we change this Curl's equation to we change the Curl equations to Maxwell's equation in just 1D, and over here is our dielectric constant value. And then again, we perform this again the central difference scheme on this particular set of equations. So you can look this our second Maxwell equation remains unmodified, and we just so we'll follow all these steps again for this particular equation. So upon including the epsilon r value, our equation will again include the epsilon r value over here. This remains unchanged. And then for these two equations, we get these two equations. So these are our MATLAB Python compatible update equations. And over here, so you can see this thing is over here. So over here, we are including our coefficient values as CB, where CB is equals to 0.5 by epsilon. So what happens is when writing our code, you have this our simulation spaces here. We have our ABC over here. We have our ABC over here. There are different. We have all our nodes again over here. And now for to define a dielectric body over here, what we do is we use CB as the coefficient. So CB equal to CBK. So CB0, CB1, for example, for MATLAB, this is 1, this is 2, this is 3, this is 4, this is 5, So we should have a 5 over here. 5, 6, 7, let it be 12. Then again, we'll have a 13 outside this region, 14, and again till K it will go. So what we do is we assign CBK as, so this CB will be 0.5, and uh, this is epsilon, right? This is epsilon r. So this will be 0.5 in this region, and we'll include the dielectric constant over here. So we'll have 0.5 for, and if this particular region has a dielectric constant of 4, this will be 0.5 by 4, which will be 0.125. So CB will be 0.125 in this region, and then again 0.5 in this region. So for the entire space, we have given a dielectric profile, which includes this free space region, this dielectric region, and this then again the free space region. So once you have given this, and then we'll use these update equations only, and we'll see that the dielectric has been included in our 1D profile, or the 1D simulation region. Okay, so yes. Yeah, so this is all about including a dielectric medium in 1D simulation space. Questions? Any questions you have?
There was no change in the update equation of magnetic field. Achha, okay, it's
Yeah.
dielectric.
Since only the dielectric constant is changing, there is no change. But if mu r were to change, the second equation
Then
will also change. Then.
yes.
Yes. Any follow-up questions, Abhishek, on this?
And in the diagram which is shown in the right side, you mentioned the boundary
Yes.
between fourth and fifth cell. So it is like a convention that we put it in between, or we can also put it on the boundary of the fourth cell or fifth cell, something like that.
Yeah, so it can be, for example, in this case, if we are considering uh, we are assigning the CB equal to 0.125 on fifth, right? So essentially, our code is only seeing this particular region as the dielectric. So yeah, so this happens. So there will always be some approximation, right? So for example, if our dielectric were to start over here and and end over here, so we'll have to assign the values at the nodes. So it could be on the boundary, but then again we are losing the space. So this happens. So if you use a finer cell size, you will be able to better approximate the electric region, and it is fine if this particular node 5 lies on the boundary or lies inside the boundary, you will assign it equal to 0.125 epsilon, 0.125 value.
Okay.
Any further questions? So code for this I won't be sharing now. This will be part of your assignment that I've already given you the update equations over here. You'll have, you can modify the code, include the electric profile before you start, before the main part of the code, modify the update equations inside the main part of the code, and you will be able to simulate your dielectric region. Okay. Now, till now we have seen wave propagation in free space, wave propagation in a dielectric media. Now, we do have mediums, like all mediums are lossy. So what happens if they are lossy? So the loss term is specified by conductivity. So this is known to us. Now, up till now, our Maxwell equation initially did not consider epsilon r. Then we included the update equations for epsilon r. Now we're again including conductivity, which is the loss term for uh, for our case. Yeah, so this is the Maxwell's equation, like the so till now, when we were considering the Maxwell's equation, we were ignoring this term. We were ignoring this term, and this was our Maxwell's equation. Now we are since we want to include the loss term, we want to include the conductivity. So we allow we add we do not ignore the current density term. From the microscopic ohmic law tells us that J can be expressed at sigma times E, where sigma is the conductivity. So substituting this particular value over here, we get this we get the one dimensional our Maxwell's equation, the Curl's equation, as in this form. So over here, our electric field is dependent upon the sorry, this is not the one dimension. So we get our electric field is dependent upon the magnetic field, and again this electric field. Now we have to rewrite our um, update equation, which using the central difference scheme to include this particular term. Okay, so reverting back to our one-dimensional term, so our electric field. So again, the electric field is in the x direction, the magnetic field is in y direction. Uh, and this is our Maxwell's equation when we included the loss term, which is the conductivity. Now, performing central difference. Okay, so first we make a change of variables. So yeah, we do that. We have we also did it earlier when we wanted to reduce the order of magnitudes between the electric and magnetic field. So we perform the change of variables. And yeah, so after using the central difference scheme again, so this is and this are same what we had earlier, and now we have this additional term over here. So this term translates to this term over here, and then translates to this term over here. Since since are the first term, the first two terms, this was a time derivative, this was a space derivative, but this is not a derivative. But again, we do not know the value of electric field at n. We have the electric field value at n plus half. We have the electric field value at n minus half. So what we do is we take the average of the value of electric field at time instant n plus half and n minus half. We divide it by 2. That is, we take the average, and then we get the update equation for the electric field, which includes the loss term. So you can notice that the last term is approximated as average across two time steps. So this is the first time step, and this is the second time step. So we are averaging the electric field values to get the electric field value at equal to at En. Yeah. So any questions till now? Next steps will simplify and write the update equation for MATLAB and Python using the update equation over here. Okay, I'll go over it again. So what we did is we started with the Maxwell's equations, which included the current density, and we expressed the current density in terms of conductivity, and the conductivity specifies the loss term of a media. So then after including this conductivity over here, we made a change of variables, and then we wrote uh, the updating we wrote the partial differential equation using central difference scheme. And since the last term was not actually not actually a derivative, we just used the average of the electric field at time instant n plus half and n minus half to approximate the value of electric field at n at En. Now, using this particular equation, so up till now, we all our equations were using this the equation till this part. Now we have gained this part for the including the loss term. Now simplifying it for n plus half, we have n plus half over here. So we simplify it. So we bring all the en plus half term over here. Its coefficient is 1, its coefficient is this value. So the coefficient over here, and keeping this n minus half term over here, this term comes over here, and this particular th terms come over here. Okay, so this comes over here. So simplifying it, and then again use we calculating this value equal to half. We substitute this over here. So and then again dividing by this coefficient over on both the sides over here. So we get the electric field at n plus half in terms of electric field at a previous instant, including the loss term over here. So if there were no losses, these two terms will become 0, and will have just have this particular value, and again this term will become 0, and will revert back to to the previous condition where we do not have any losses. So over here sigma is included, which includes the losses. And so till now we derived the electric field expression. The magnetic field expression remains unchanged because it did not have the sigma term. So we had already derived it in the previous slides. So now we have the electric field and magnetic field update equations in terms of loss and electric permittivity. So using these two equations, we can write the computer compatible update equations. So we define this as CA, this as CB. So CA and CB are over here. And so we define EAF as dt by sigma 2 times epsilon z epsilon naught. So this particular term is defined as EAF. So CA is equals to 1 minus EF by 1 plus EF over here. CB equal to 0.5 by epsilon times 1 plus EF over here. So now we have the update equations for a media which is lossy and has a dielectric constant. Now, yeah, so this is all for a lossy medium, lossy dielectric medium, and we in the previous slide we discussed about propagation in a dielectric medium. So till now we have covered we started with free space. We included dielectric media, and now we studied about propagation in a lossy dielectric media. So this concludes our module 2. I'll take any questions that you had till now regard from the previous class, today's class, any confusion with the update equations that we discussed right now, especially the lossy dielectric media.
And are we going to discuss MATLAB code next class, right? For this part?
Yeah. So today, I've given you this. I'll give you the codes. I'll let you guys try using since the update equations are already here. So you can see, follow the lecture. Try to use this. If you are able to do it, then it is very great that you have that you are able to modify it like according to the simple for a free space to dielectric constant. If not, then we'll again discuss it in the next class for the lossy dielectric media as well.
Yeah, and you mentioned for the code for free space, you mentioned that you will give some assignment, and
Yes.
we can play around and just to learn more code. I think that's the best idea. So are you going to send the assignment after the class by email or?
Yeah. Yeah, I'll upload the assignment on the IEEE portal and again in the email as well, because some of you do not have
Yeah.
the access to IEEE till now. So yeah, so we'll
Yes.
discuss the assignment questions now itself only, so that you don't have to worry about it during this coming week. So
Okay.
so far, so today, for in conclusion, like we have till now we had till last class we had discussed the one-dimensional free space simulation. We discussed the stability, the boundary conditions, how do we determine the cell size. We looked at the code. We saw soft source, hard source. Again, how do we include a sine source? That is also an assignment. We saw propagation in dielectric medium and the lossy dielectric medium. Okay. So this was all that was covered today. Any questions from what was covered today? Jay, any questions? What from like any topic that you want to like we can go back and discuss now? And
Not today. It was really amazing. I understood most of the things.
oh,
So when I
any
will run the
questions?
when I will run the MATLAB code
Yes.
based on assignment, then I will ask many questions. Not today.
Yeah, yeah, sure. That will be good. Any
Yeah.
questions, Priyank, Santha, Abhishek, Anusha, Deva Prasad?
No, no, it was fine. You can go ahead.
Okay. So so we have we're done with the module 2. Next class will start with module 3 and discussion of the assignment. So module 3 is like we have already discussed all the lossy dielectric media. So module 3 will the important topic that we will covering is this frequency dependent media, and brief will look at the reformulation. Use instead of using electric field, we'll use the electric flux density, and instead of E, we'll use D. We'll develop code with that, and we'll also look at the frequency domain output, because right now we are looking at all the time domain results, and it is important that we also know how to get the frequency domain results. For example, looking at sinusoidal waves or sum of sinusoidal waves, we won't be able to know which frequencies they are at. So what we'll do is we'll use facilities from MATLAB, the FFT part, and do an FFT on the time domain data that we are getting you from the codes that we developed today. So this is the first assignment. So I'll give you the MATLAB code that we saw today. I want every one of you to at least run this code, go through each line. The second task will be to you comment the absorbing boundary conditions and see what happens on the boundaries. And it will be good if you try to like analyze it, like uh, why the reflections are not the same on each boundary. Otherwise, we'll discuss your interpretation, and again we'll I'll try to share mine. Uh, the third task would be that you like I've already shown you with simulation space with two sources. Um, so you also try to include the two sources at kc minus 20 and kc plus 20, and what happens like try to comment on what happens when the two pulses meet. Um, the fourth task will be that you try to include this is very essential, that you try to include a dielectric material of a slab from kc minus 50 to kc plus 50, and just keep one source at kc minus 100. So there will be a source which forms a Gaussian pulse which will propagate towards this particular slab, and like try to observe what happens when the pulse hits the slab and travels through it. Then next will be that you modify the second code, the question, this particular code which you developed in question 4 for a lossy dielectric material. So again, there will be a dielectric slab from Kc minus 50 to Kc plus 50. There's a Gaussian pulse source at Kc minus 100, and this pulse will travel towards this slab, hit the slab, and propagate through it. Now you have to observe what difference is there when it travels to a free space, when it travels to a dielectric material without any loss, and a lossy dielectric material, like how the pulse changes inside this lab. So this will be and then you can modify the pulse, the source excitation. Instead of using a Gaussian pulse, you can include a sinusoidal pulse, a sinusoidal source, and see what happens. So already most of the material has already been given in this slide. You can use them, and if you have any doubt, you can email me during this week. It is not necessary that you finish it by the next class. It is fine. We'll discuss till what you are comfortable with. If somebody wants to still try it by the next class, it is fine. We'll discuss how much everybody has done. And an important announcement: we will have class on 24th. We won't have any class on 25th as it is Christmas. Okay, and on 24th we'll decide whether do we want a class on New Year or before or after New Year. We'll see. So, any questions on the assignment?
Not from my side. It's fine.
Okay. Also about the assignment, if you can also look at the book by Dennis and Sullivan. So the questions and answers are also available over there. So if you are able to solve it, maybe you can reference try to read the book, and you and check your results with the book. If you have done it and you don't want to wait till the next class. And also, since we have already done with module 2, so we have already covered chapter 1 from the Dennis and Sullivan book. So you can go through the text and see if you have any doubts. Okay, so I'll wait for some time. Maybe you can go through the questions, and we can discuss if you have any doubts. Any questions, Deba Prasad? I believe you joined a little late. Were you able to follow the lecture? Okay, maybe there's some connection issue. So the record, I'll upload the recording by the end of day. I'll upload the slides as well and send out the assignment, and share the MATLAB file, the .m file itself, so you can directly run it on MATLAB. And if you need any other help, you can email me, and we'll meet on the next class, which is on, I believe, the next class is on 24th. So we'll meet on 24th, and we'll discuss when we meet next. So if nobody has any questions, we can end the class for today.
Yeah, okay. Thank you so much. Really appreciate. Thanks.
Thank you. Thank you.
Yeah.
Thanks, Anand.
Yeah, you're welcome. So I'll stop the recording now.